The universe should not exist. Not in the sense that it is improbable or surprising or difficult to explain, in the more fundamental sense that if the laws of physics are what we think they are, and if the Big Bang worked the way we think it worked, then the universe that resulted should have been completely empty within the first second. Every particle of matter produced in the initial fireball should have found its antimatter partner within that first second. The two should have annihilated in a burst of pure energy, and the universe should have settled into a featureless bath of radiation, expanding outward into a void that contained nothing. No atoms, no molecules, no dust, no stars, no galaxies, no planets, no oceans, no chemistry, no biology. The universe should be light and darkness and nothing else, stretching outward forever, containing not a single particle of matter in all its observable volume. Instead, here you are, reading these words which were written by a brain made of atoms, transmitted to your eyes or your ears through devices made of atoms, processed by neurons made of atoms, generating thoughts in a mind that, whatever it is, requires atoms to function. You exist, and everything you have ever touched or seen or thought about exists because of a deviation from perfect symmetry that was smaller than 1 part in a billion. For every billion pairs of matter and antimatter particles produced in the Big Bang, there were 1,000,001 matter particles. The billion pairs annihilated. The one matter particle survived. That 1 in a billion surplus, accumulated across the entire fireball of the early universe, is everything. The stars, the planets, the oceans, the cells, the people. Every structure that has ever existed in the universe is the residue of an asymmetry so tiny that it is almost nothing, built on an imbalance so small that it took decades of the most sophisticated experiments in the history of physics to begin to understand where it comes from. We do not fully understand it yet. We know it exists. We are the proof of its existence. We know roughly what kind of physics is required to produce it. We do not know the specific mechanism. The experiments searching for that mechanism are among the most extraordinary scientific enterprises of the current era, and what they are finding is beginning to change the picture. But the answer is not in hand. The question of why the universe contains matter, why anything exists, is still open. And the fact that it is still open after a century of physics that has successfully answered questions of comparable depth about the structure of matter and the forces of nature tells you something about how hard it is. The story of antimatter begins not with an experiment, but with an equation. And the story of the equation is one of the most remarkable in the history of science because of how it was found and what it said when it was found. Paul Dirac was born in Bristol in 1902, the son of a Swiss father who taught French and an English mother who worked as a librarian. His father, Charles Dirac, was by all accounts a difficult man. He enforced a rule at the dinner table that Paul and his siblings could only speak to him in French, as a language lesson. And since Paul's French was imperfect, the practical consequence was that Paul said almost nothing at dinner, year after year. Some biographers have suggested that this enforced silence contributed to the legendary taciturnity that characterized Dirac as an adult. He was famously a man of few words, precise and economical in speech to a degree that his colleagues found remarkable. When complimented on a paper, he might respond with a single yes. When asked if he had enjoyed a film, he might calculate the answer literally. The film was 90 minutes long. There were so many characters, the ratio of talking to action was such that his assessment was delivered as a brief technical evaluation. But inside this silent exterior was one of the most extraordinary mathematical minds that physics has ever produced. Dirac entered the University of Bristol at 16, completed an engineering degree, found no work during the post-war depression, and then enrolled in mathematics at Cambridge, where he encountered quantum mechanics, the new physics of the atomic world that was being developed simultaneously by Heisenberg in Germany and Schrödinger in Austria, and that Dirac himself would reformulate in a more powerful and more elegant mathematical framework that unified the two apparently different approaches. In 1927, Dirac was 25 years old and was sitting with a problem that had been nagging at him. Schrödinger's wave equation, the equation that described the quantum behavior of the electron, was not consistent with special relativity. It treated space and time differently, which violated the requirement that the laws of physics should look the same to any inertial observer. Dirac wanted to write a quantum mechanical equation for the electron that was relativistically covariant, that treated space and time on equal footing, as Einstein's theory required. This was not a simple task. The obvious approaches did not work. They produced equations with solutions corresponding to negative probabilities, which is physical nonsense. Dirac tried a different approach. He looked for an equation that was first order in time, like the Schrödinger equation, rather than second order, in the hope that this would avoid the negative probability problem while still satisfying the requirements of special relativity. What he found, in 1928, was the equation that bears his name. The Dirac equation is one of the most beautiful equations in physics, compact, elegant, and extraordinarily powerful. It described the quantum behavior of the electron in a way that was fully consistent with special relativity. It automatically predicted the spin of the electron, the intrinsic angular momentum that had previously been added to quantum mechanics as an extra assumption, as a consequence of the mathematics rather than as a separate postulate. It predicted the magnetic moment of the electron with a precision that had not been achieved before. By any measure, it was an extraordinary achievement, but it had a problem. Or what looked like a problem. The Dirac equation had 4 solutions where there should have been 2. For an electron moving in a given direction, there were 2 solutions with positive energy, corresponding to the electron with spin up and spin down, which was expected and correct, and 2 solutions with negative energy, which was not expected and not obviously physical. A particle with negative energy was deeply strange. It could in principle keep radiating energy forever, spiraling down into more and more negative energy states without limit. This would be catastrophically unstable. Dirac knew this, and he struggled with what to do about the negative energy solutions. His first attempt at a resolution was ingenious but ultimately unworkable. He proposed that all the negative energy states in the universe were already filled, that there was a vast invisible sea of negative energy electrons, everywhere in space, all the quantum states already occupied. Because electrons obey the Pauli exclusion principle, no 2 electrons can occupy the same quantum state. A positive energy electron could not fall into a negative energy state because all the negative energy states were already taken. The Dirac sea, as it came to be called, was Dirac's attempt to make the negative energy solutions physically harmless by making them inaccessible. But the Dirac sea had a further implication that Dirac realized in 1930. If the sea of negative energy electrons was everywhere, what happened if one of the negative energy electrons absorbed enough energy to jump to a positive energy state? It would leave behind a hole in the sea, a vacancy in the negative energy states. This hole would look, to any observer, like a particle with positive energy and positive charge, the opposite charge to the electron. It would be, in every measurable way, an electron with positive charge. Dirac initially tried to identify this hole with the proton, the only positively charged particle known at the time, but the mathematics would not allow it, because the proton is about 1836 times heavier than the electron, and the hole had to have the same mass as the electron. In 1931, backed into a corner by his own mathematics, Dirac made the prediction explicit. There must exist a particle identical to the electron in mass but opposite in charge. It had not been observed. It should exist. He called it the anti-electron. The physics community's reception was mixed. Some found the prediction compelling. It came from an equation that had already made several correct predictions, and the mathematical logic was unavoidable. Others found it embarrassing. It seemed to suggest that half of all possible particles were yet to be discovered, and the Dirac sea was a strange and unwieldy construction. Einstein himself, when told about Dirac's equation, is reported to have said that it was not possible to derive so much from so little, and that the results seemed almost too good to be true. The prediction was out there. The question was whether the anti-electron existed. Carl David Anderson was an experimentalist at Caltech, working with cloud chambers to study cosmic rays, the high-energy particles from space that constantly rain down on Earth's atmosphere, producing cascades of secondary particles that could be detected and studied. A cloud chamber is a container filled with supersaturated vapor, in which the ionizing track left by a charged particle produces a visible trail of droplets, like the contrail behind an aircraft, but at the scale of individual particles. Anderson had a cloud chamber surrounded by a powerful electromagnet, which curved the tracks of charged particles. The radius of curvature depended on the particle's momentum, and the direction of the curve depended on the sign of its charge. By placing a lead plate across the middle of the cloud chamber, he could determine which direction a particle was moving. A particle passing through the lead plate would lose energy and therefore have a smaller radius of curvature after the plate than before it, allowing Anderson to determine the direction of travel and therefore the sign of the charge unambiguously. In August of 1932, Anderson photographed a particle that curved the wrong way. It had the same curvature as an electron, the same mass, moving at the same speed, but it curved in the opposite direction. It was a positive electron, the anti-electron. Dirac's prediction confirmed. Anderson named it the positron, and the name stuck. He published the result in September 1932, and it was received with the astonishment it deserved. A particle that had been predicted purely from the mathematics of a relativistic quantum equation, with no experimental evidence beforehand, with no theoretical motivation beyond the internal logic of the equation, had been found exactly as predicted. The anti-electron existed. Dirac's equation had not been wrong. The negative energy solutions were real. The implications took time to sink in because the full implications were breathtaking. If every particle of matter had an antimatter twin, if the mathematics that produced the anti-electron was as universal as it appeared, then the proton had an antiproton, the neutron had an antineutron, and in principle every subatomic particle had an antiparticle identical in mass but opposite in all charges. Antimatter was not a curiosity or an exception. It was a fundamental feature of any quantum mechanical description of a relativistic universe. The universe was, according to theory, symmetric between matter and antimatter. The laws of physics, as written, did not prefer one over the other. This prediction was confirmed as particle accelerators became powerful enough to produce antiparticles artificially. The antiproton was created at the Beavatron accelerator at Lawrence Berkeley National Laboratory in 1955 by Emilio Segre and Owen Chamberlain. They received the Nobel Prize in Physics in 1959. The antineutron was created shortly after. As accelerator energies increased, antiparticles of every known particle were produced and studied. The pattern was universal. Every particle had its antiparticle. The standard model of particle physics, which eventually unified the strong, weak, and electromagnetic forces in a single theoretical framework, embedded the matter-antimatter symmetry, called charge conjugation symmetry or C-symmetry, as a fundamental principle. The theory was symmetric between matter and antimatter. The particle physics equations were mirror images in this respect, and yet, and this is the fact that everything else in this story turns on, the universe is not symmetric between matter and antimatter. The universe is overwhelmingly made of matter. Every star, every planet, every atom you have ever encountered is matter, not antimatter. There is no antimatter sun in our solar system, no antimatter galaxy in our local group, no antimatter supercluster in the observable universe. When cosmic ray physicists study the particles arriving from space, particles that have traveled across the galaxy and beyond, they find particles of matter, not antimatter, in overwhelming abundance. The antiprotons they do find are consistent with being produced by the collision of cosmic rays with interstellar gas. They are secondary products, not evidence of primary antimatter regions in the universe. The universe is made of matter. The theory says it should be symmetric. It is not. Something broke the symmetry. This is the matter-antimatter asymmetry problem, and it is one of the deepest unsolved problems in fundamental physics. Its solution requires understanding not just the physics of individual particles, but the physics of the early universe. The physics of the first fractions of a second after the Big Bang, when the universe was hot enough to produce particles and antiparticles in enormous numbers, and when the tiny asymmetry that would eventually produce everything we see was somehow imprinted on the cosmos. The framework for thinking about this problem was provided by the Soviet physicist Andrei Sakharov in 1967, the same Sakharov who would later become a dissident and a Nobel Peace Prize laureate, who had been one of the designers of the Soviet hydrogen bomb and whose conscience eventually led him to publicly oppose the weapons he had helped build. In 1967, Sakharov published a remarkable paper in Jet P Letters, a Russian physics journal, in which he identified 3 conditions that any theory of the early universe must satisfy in order to produce a universe with more matter than antimatter. These conditions are now called the Sakharov conditions, and they are: first, there must be processes that violate baryon number, that convert baryons, protons and neutrons and their combinations into non-baryons or vice versa. If baryon number is perfectly conserved, the excess of baryons over antibaryons in the universe cannot change. It was set at the initial moment and stays fixed. If the initial conditions of the Big Bang produced equal amounts of matter and antimatter, and if baryon number is conserved, then matter and antimatter must remain equal forever, and the universe is empty. To generate a net baryon number from an initially symmetric universe, you need processes that violate baryon number conservation. Second, there must be violation of C-symmetry and CP symmetry. C symmetry is the symmetry between particles and antiparticles. If C symmetry is exact, then every process that creates a baryon also creates an antibaryon at the same rate, and no net baryon number is generated. CP symmetry is the combination of charge conjugation, C, and parity, P, parity being the symmetry between a process and its mirror image. If CP symmetry is exact, then even with baryon number violation, the rates of baryon-producing and antibaryon-producing processes are equal, and no asymmetry is generated. To produce more matter than antimatter, the laws of physics must treat matter and antimatter differently. CP symmetry must be violated. Third, these processes must occur when the universe is out of thermal equilibrium. If the universe is in perfect thermal equilibrium, then for every process producing baryons, the reverse process, which would consume baryons, occurs at exactly the same rate, regardless of whether C or CP is violated. Net baryon production requires a departure from equilibrium, which naturally occurs during phase transitions in the early universe, when the universe is cooling rapidly through temperatures at which different interactions are important. Sakharov's conditions are elegant and general. They do not specify the mechanism, they only identify what any mechanism must satisfy. The question of whether the standard model satisfies all three conditions is the question of whether the standard model can explain the matter-antimatter asymmetry of the universe. It can satisfy two of them. Baryon number violation is present in the standard model through a process called Sphaler-on transitions, which involve non-perturbative effects of the weak force that can convert baryons into leptons and vice versa. These processes were rapid in the hot early universe and become negligible at temperatures below about 100 GeV. The electroweak phase transition, the transition at which the Higgs field acquired its vacuum expectation value and the W and Z bosons became massive, provides the departure from thermal equilibrium required by Sakharov's third condition. The second condition, CP violation, was discovered experimentally in 1964 by James Cronin and Val Fitch at Brookhaven National Laboratory, in a result that won them the Nobel Prize in Physics in 1980, and that is one of the most important discoveries in the history of particle physics. Cronin and Fitch were studying the decay of particles called neutral kaons, mesons containing a strange quark and an anti-down quark, or vice versa. Neutral kaons come in two types, K-long and K-short, which have different lifetimes and different decay modes. The prediction of CP symmetry was that K-long kaons should decay only into 3 pions, never into 2 pions. The 2-pion decay mode was predicted to be forbidden by CP symmetry. Cronin and Fitch observed K-long kaons decaying into 2 pions. The forbidden decay was happening. CP symmetry was violated. The universe, at some level, was treating matter and antimatter differently. The discovery was a sensation. CP violation was not predicted by any theory at the time, and its existence required the extension of the theoretical framework. In the standard model, CP violation arises through a complex parameter in the CKM matrix, the matrix that describes the mixing of different quark flavors, and it is characterized by a phase angle that is non-zero. The existence of CP violation in the standard model was eventually understood to require at least 3 generations of quarks, a point that Makoto Kobayashi and Toshihide Masukawa realized in 1973 when they showed that CP violation in quark mixing requires a matrix of at least 3 by 3, which requires at least 3 quark generations. At the time, only 2 quark generations were known. The third was discovered in 1977 with the observation of the bottom quark. Kobayashi and Masukawa received the Nobel Prize in Physics in 2008. But here's the problem. The CP violation in the standard model is not enough. The amount of matter-antimatter asymmetry in the universe, the 1 part in a billion excess of matter over antimatter, requires a certain magnitude of CP violation in the processes that generated it in the early universe. The CP violation in the standard model, as measured in kaon and B-meson decays, is orders of magnitude too small to account for the observed asymmetry. It is in the right direction, it breaks the matter-antimatter symmetry, but the effect is too small by many orders of magnitude. The standard model, even with its CP violation, cannot explain why we exist. Some additional source of CP violation, some physics beyond the standard model, is required. This is the central experimental challenge that drives the most sophisticated particle physics experiments studying matter-antimatter asymmetry. Where is the additional CP violation? What process, what new particles, what new forces produce the additional asymmetry that the standard model cannot account for? The answer is hidden somewhere in the data, waiting to be found by experiments sensitive enough to see it. The B-factory experiments, Bell at the KAK accelerator in Japan and Babar at the SLAC accelerator in California, were specifically designed to study CP violation in the decays of B mesons, particles containing a bottom quark, with a precision that would test the Standard Model's predictions and potentially reveal new physics. They ran throughout the 2000s and produced an extraordinary amount of data. The results confirmed the Standard Model's predictions for CP violation in B meson decays to impressive precision. The CKM framework, the Kobayashi-Maskawa mechanism, was confirmed as the correct description of CP violation in quark flavor-changing processes. But the confirmation of the Standard Model was not the answer physicists were hoping for. It confirmed that the mechanism was right, but the magnitude was wrong. Additional CP violation from outside the Standard Model had not been found. The experiments were looking in the right place, but the new physics was not there, or at least not in the channels these experiments were sensitive to. The Bell 2 experiment, a successor to Bell currently running at the Super KKB accelerator in Japan, is pursuing the search with higher luminosity, producing more B mesons and therefore more statistical power to detect small deviations from the Standard Model's predictions. The LHCb experiment at the Large Hadron Collider at CERN is studying CP violation in B mesons, D mesons, and baryons containing heavy quarks with extraordinary precision, looking for any deviation from the Standard Model predictions that might point to new physics. As of the mid-2020s, both experiments are producing results consistent with the Standard Model, with some hints of possible anomalies that are being actively studied. The new physics has not yet been definitively found, but there is another approach to the problem that is more direct and potentially more powerful. And it is the approach that has produced some of the most extraordinary experiments in the history of physics. Instead of studying CP violation in the decays of hadrons containing heavy quarks, you can study antimatter directly. You can make anti-atoms, trap them, and compare their properties to the equivalent matter atoms with the highest possible precision. If the laws of physics are truly symmetric between matter and antimatter, then an antihydrogen atom, a positron bound to an antiproton, should have exactly the same spectrum, the same energy levels, the same transition frequencies as an ordinary hydrogen atom. If there is any asymmetry, if the laws of physics treat matter and antimatter differently in any way, then the spectrum of antihydrogen will differ, by however tiny an amount, from the spectrum of hydrogen. Measuring that spectrum with sufficient precision is the goal of the ALPHA experiment at CERN, and the precision that has been achieved is extraordinary. Making antihydrogen is not simple. It requires first producing antiprotons, which is done at CERN's antiproton decelerator, a storage ring that takes antiprotons produced in high-energy proton-proton collisions, collects them, and slows them from nearly the speed of light to a few % of the speed of light, where they can be trapped and used. It then requires producing positrons, which are relatively straightforward. Radioactive sodium-22 produces positrons when it decays, and they can be collected and accumulated in a penning trap, a device that confines charged particles using a combination of electric and magnetic fields. Mixing cold antiprotons and positrons in the right conditions allows them to combine to form antihydrogen atoms. But antihydrogen, as a neutral atom, cannot be confined by electric fields. It can only be confined by magnetic fields, specifically by the gradient of a magnetic field that acts on the magnetic moment of the atom, creating a potential energy minimum at a specific location. This is an extremely shallow trap. The depth corresponds to a temperature of only about half a Kelvin, meaning that any antihydrogen atoms with more kinetic energy than this will escape the trap and annihilate on the walls. Making antihydrogen cold enough to be trapped is a formidable technical challenge. The ALPHA collaboration, led by Canadian physicist Geoffrey Hangst, achieved the first trapping of antihydrogen in 2010, 38 antihydrogen atoms, trapped for 172 milliseconds. This was followed by improved results, larger numbers, longer trapping times, until antihydrogen could be trapped and held for thousands of seconds, long enough to perform precision spectroscopy. In 2012, the ALPHA collaboration performed the first spectroscopic measurement of antihydrogen, using microwaves to drive transitions between the hyperfine ground states of the trapped anti-atoms. In 2016, they performed laser spectroscopy of antihydrogen for the first time, measuring the 1s-2s transition, the two-photon transition between the ground state and the first excited state, with a precision of 2 parts in 10 to the 10th. This is the same transition that has been measured in ordinary hydrogen with extraordinary precision, and it is the transition from which the most demanding tests of quantum electrodynamics are derived. The comparison of the 1s-2s transition frequency in hydrogen and antihydrogen is therefore one of the most precise tests of CPT symmetry, the combined symmetry of charge conjugation, parity, and time reversal, ever performed. CPT symmetry is a theorem in quantum field theory that says all local Lorentz invariant quantum field theories must be symmetric under the combined transformation of C, P, and T simultaneously. If CPT symmetry is violated, the foundations of quantum field theory must be wrong. If it is exact, the spectrum of antihydrogen must be identical to the spectrum of hydrogen. The result: the 1s-2s transition in antihydrogen agrees with hydrogen to a precision of 2 parts in 10 to the 12th. The spectra are identical. To this precision, CPT symmetry holds, at least at this level. This is both a profound confirmation of the foundations of physics and a somewhat frustrating result for the matter-antimatter asymmetry problem. If CPT is exactly conserved, the routes to matter-antimatter asymmetry are more constrained. But alpha has gone further. In 2023, the collaboration performed the first measurement of the Lyman-alpha transition in antihydrogen, the 1s-2p transition, which is the fundamental ultraviolet transition of hydrogen and the most intense spectral line of hydrogen in the universe, responsible for much of the absorption seen in quasar spectra. The measurement confirmed that the Lyman-alpha transition frequency in antihydrogen is consistent with that in hydrogen to the precision achieved, and the collaboration has performed experiments measuring the effect of gravity on antihydrogen. Does antihydrogen fall down, like matter, or does it fall up? This is a question that may seem obvious, but in fact the general relativistic coupling between matter and antimatter is not well constrained by theory alone, and some models of quantum gravity allow for a difference in the gravitational response of matter and antimatter. The alpha-G experiment, which oriented the magnetic trap vertically and allowed antihydrogen to escape from one end or the other under the influence of gravity, produced in 2023 the first direct measurement of the gravitational acceleration of antihydrogen. The result: antihydrogen falls down like matter with an acceleration consistent with the ordinary gravitational acceleration of 9.8 meters per second squared. Antimatter does not fall upward. Gravity is not the source of the matter-antimatter asymmetry. The base experiment at CERN takes a different approach. Instead of making and studying neutral anti-atoms, it traps antiprotons in a Penning trap and measures their fundamental properties, their charge-to-mass ratio, and their magnetic moment, with extraordinary precision, comparing them to the equivalent measurements on protons. The charge-to-mass ratio of the antiproton and the proton have been compared to a precision of 69 parts per trillion, a measurement so precise that it has required the development of new experimental techniques for measuring the cyclotron frequency of a single trapped particle. The magnetic moment of the antiproton has been measured and compared to the proton magnetic moment, with a precision of 1.5 parts per billion. In every comparison, the antiproton and proton are equal and opposite to the precision achieved. CPT symmetry holds at the level tested. The neutrino sector is another place where matter-antimatter asymmetry might be hiding, and it is currently one of the most actively studied areas in particle physics. Neutrinos, the nearly massless, weakly interacting particles that are produced in radioactive decays and in nuclear reactions and that pass through ordinary matter with minimal interaction, come in 3 flavors: electron neutrino, muon neutrino, and tau neutrino. In the 1990s and 2000s, experiments detected a phenomenon called neutrino oscillation, the spontaneous conversion of neutrinos from one flavor to another as they travel through space. Neutrino oscillation requires neutrinos to have non-zero masses, which was a surprise since the standard model predicted massless neutrinos, and it requires the neutrino mass eigenstates to be different from the neutrino flavor eigenstates, exactly analogously to the quark mixing described by the CKM matrix. The equivalent for neutrinos is the PMNS matrix, named after Pontecorvo, Maki, Nakagawa, and Sakata. Just as the CKM matrix has a complex phase that produces CP violation in quark processes, the PMNS matrix has a complex phase, called delta CP, that would produce CP violation in neutrino oscillations. If delta CP is non-zero, the neutrinos oscillate differently from antineutrinos. A muon neutrino traveling through the Earth would convert to an electron neutrino at a different rate than a muon antineutrino traveling the same distance. Measuring delta Cp is one of the most important goals in current particle physics, because Cp violation in the neutrino sector could be large, potentially much larger than the Cp violation in the quark sector. And because the lepton sector provides an entirely different possible source of the matter-antimatter asymmetry through a mechanism called leptogenesis. Leptogenesis is the idea that the matter-antimatter asymmetry in the universe was not generated directly in the baryon sector, in the quarks and protons, but was first generated in the lepton sector, in the neutrinos and electrons, and was then transferred to the baryon sector through the Sfalerion processes that the standard model predicts. In many models of leptogenesis, the key players are very heavy right-handed neutrinos, particles beyond the standard model that are predicted by the seesaw mechanism for generating the small but non-Seer masses of the known left-handed neutrinos. These heavy right-handed neutrinos, produced abundantly in the hot early universe, would decay with different rates into leptons and antileptons if the relevant Cp violation is large enough, generating a net lepton number asymmetry. The Sfaleron processes then convert this lepton asymmetry into a baryon asymmetry, the matter-antimatter asymmetry that we observe today. The delta Cp parameter of the PMNS matrix is related to this leptogenesis mechanism, not directly because the specific Cp violation that drives leptogenesis involves the heavy right-handed neutrinos that have not been observed, but there is a connection in specific models. Measuring delta Cp in neutrino oscillation experiments does not directly measure the Cp violation relevant to leptogenesis, but it is a measurement of Cp violation in the lepton sector that constrains the broader theoretical framework. The two major experiments measuring delta Cp are T2K in Japan and NOVA in the United States. T2K, Tokai to Kamioka, sends a beam of muon neutrinos or muon antineutrinos from the J-Park accelerator facility in Tokai, on the Pacific coast of Japan, to the Super Kamiokande detector in the Kamioka mine, 295 kilometers away. By measuring the rate at which muon neutrinos convert to electron neutrinos, and comparing this to the rate for muon antineutrinos converting to electron antineutrinos, T2K can measure delta Cp. The results from T2K, accumulated over many years, have hinted strongly at a non-Zeur delta Cp. The data suggests that neutrinos oscillate more readily than antineutrinos, which corresponds to a value of delta Cp near -90 degrees. This would be a large Cp violation in the neutrino sector, significantly larger than the Cp violation in the quark sector. The statistical significance of the T2K result has been around 3 sigma, suggestive but not definitive. NOVA, NUMI off-axis electron neutrino appearance, sends a beam from Fermilab in Illinois to a detector in Ash River, Minnesota, 810 kilometers away. NOVA's results have shown some tension with T2K. The two experiments' preferred values of delta Cp are not entirely consistent, which has generated considerable discussion in the neutrino physics community about possible systematic effects and about whether the tension reflects an incomplete theoretical understanding of the experiments. Both experiments are ongoing, and their precision is improving. The Hyper Kamiokande experiment in Japan, a massive upgrade of Super Kamiokande with a water Cherenkov detector 50 times larger, began construction in 2020 and will eventually provide the most precise measurement of delta Cp from the T2K-style beamline. The DUNE experiment, the Deep Underground Neutrino experiment in the United States, will send a neutrino beam from Fermilab to a liquid argon detector in the Sanford Underground Research Facility in South Dakota, 1,300 kilometers away, and will provide complementary measurements with different systematic uncertainties. Together, Hyper-K and DUNE are expected to definitively determine whether delta Cp is non-Zeur, and if so, what its value is. If delta Cp turns out to be large, close to -90 degrees as T2K hints, then the neutrino sector has a large Cp violation that distinguishes it from the quark sector, and leptogenesis models become more compelling. This would not be a direct proof of leptogenesis, but it would be consistent with it, and in combination with the theoretical framework and the other Sakharov conditions, it would make leptogenesis the most plausible explanation for the matter-antimatter asymmetry. There is another window on the matter-antimatter asymmetry problem that is completely different from any of the approaches described so far, and it involves not particle physics experiments but cosmology. The cosmic microwave background, the afterglow of the Big Bang that pervades all of space, carries encoded in its temperature fluctuations a record of the conditions of the early universe, and those conditions include the baryon-to-photon ratio, the ratio of the number of baryons to the number of photons in the universe, which is a direct measure of the matter-antimatter asymmetry that was generated in the first second. The Planck satellite has measured this ratio to extraordinary precision, approximately 6 times 10 to the minus 10, about 6 baryons for every 10 billion photons. This is the 1 part in a billion that I mentioned at the beginning. Every measurement of the CMB is in this sense a measurement of the matter-antimatter asymmetry of the universe, and it provides the target that any theory of baryogenesis must hit. The extraordinary smallness of this number, 6 times 10 to the minus 10, is itself a clue. It is not obviously related to any fundamental constant in the Standard Model. It is not the square of the fine structure constant, or the ratio of the proton mass to the Planck mass, or any other combination of known constants that might give a theoretically motivated prediction. It is just a number, a tiny number, that came out of the physics of the first second of the universe, and whose value any complete theory of baryogenesis must explain. Achieving this specific value, rather than 0 or something larger, requires a careful balance of the Sakharov conditions in the specific model of baryogenesis, and different models predict different values. The measurement is precise enough to discriminate between models, but not every model makes a sharp enough prediction to be tested by the CMB alone. The combination of CMB constraints and particle physics measurements is the most powerful approach to narrowing down the mechanism. The person who first stated the problem with the clarity that made it the central question it is today, who first calculated explicitly that the Standard Model's CP violation was insufficient to account for the observed baryon asymmetry, was Vadim Kuzmin, Valery Rubikov, and Mikhail Shaposhnikov, in a 1985 paper that worked out the rate of sphaleron transitions in the early universe, and showed that the electroweak baryogenesis mechanism required a first-order electroweak phase transition and much more CP violation than the Standard Model provided. Their calculation established the scale of the problem, the gap between what the Standard Model could produce and what the universe actually has, and motivated the search for extensions of the Standard Model that could fill the gap. The extensions that have been proposed are numerous. Supersymmetry, in addition to its other virtues, can provide the first-order electroweak phase transition and the additional CP violation required by electroweak baryogenesis, if the superpartner particles are at the right masses and have the right CP violating phases. The LHC's null results for supersymmetry have constrained the simplest supersymmetric baryogenesis models, but more complex versions survive. Leptogenesis, as described, can work with the heavy right-handed neutrino masses and CP violating phases, which are not constrained by any current experiment. Affleck-Dine baryogenesis, which operates through a different mechanism involving scalar field dynamics in the early universe, is another possibility. The Affleck-Dine mechanism can produce large baryon asymmetries from relatively small CP violation, which makes it easier to achieve the right magnitude, but it requires specific conditions in the very early universe that are difficult to test directly. The honest assessment is that we do not know which mechanism generated the matter-antimatter asymmetry. We know the asymmetry exists. We are the proof. We know the 3 Sakharov conditions that any mechanism must satisfy. We know that the Standard Model satisfies all 3, but with insufficient magnitude of CP violation. We know that there is CP violation in the quark sector, measured precisely. We have hints of CP violation in the neutrino sector, not yet definitively confirmed. We are searching for new sources of CP violation in experiments at the LHC and at B factories, and in antihydrogen spectroscopy, and in measurements of the electric dipole moments of fundamental particles. And we have not yet found the smoking gun, the specific measurement that definitively identifies the mechanism. The electric dipole moment searches deserve particular attention, because they are among the most sensitive probes of new CP violating physics, and because the current experimental situation is one of the most precise in all of physics. An electric dipole moment is a separation of positive and negative charge within an object, like the separation between the hydrogen and oxygen in a water molecule that makes water a polar molecule. Fundamental particles like the electron, which are point-like, should not in principle have an electric dipole moment. The charge is a point, there is no separation. But in quantum field theory, the electron is surrounded by a cloud of virtual particles, pairs of particles and antiparticles that flicker in and out of existence, affecting the electron's properties. If there is CP violation in the physics of these virtual particles, the cloud is asymmetric in a specific way that produces a tiny electric dipole moment, a minuscule separation of the electron's effective charge distribution in the direction of its spin. The size of the electric dipole moment is a direct measure of the amount of CP violation in the virtual particle corrections, and larger CP violation means a larger electric dipole moment. The Standard Model's prediction for the electron-electric dipole moment is extraordinarily small, about 10 to the minus 38 electron centimeters, far below any conceivable experimental sensitivity. But models that extend the Standard Model to include new CP-violating physics to generate sufficient baryogenesis typically predict electron-electric dipole moments many orders of magnitude larger, closer to 10 to the minus 27 to 10 to the minus 29 electron centimeters. The current experimental limit, set by the ACME experiment at Harvard, is below 10 to the minus 29 electron centimeters. This extraordinary precision, achieved by measuring the precession of electrons in a beam of thorium monoxide molecules in a precisely controlled electric field, has already ruled out a wide class of models that predicted electron-electric dipole moments above this bound. The search is not finished. A new generation of experiments, including ACME-3 and EDM experiments using trapped molecular ions, is pushing the sensitivity further, squeezing the space available for new CP-violating physics to hide. Let me describe one more experimental direction that is extraordinary in its ambition and its ingenuity: the search for neutron oscillation into anti-neutron oscillation. This is the most direct test of baryon number violation, one of Sakharov's three conditions. If baryon number is not perfectly conserved, then a neutron, which has baryon number 1, can spontaneously oscillate into an anti-neutron, which has baryon number -1, and back again, in a quantum mechanical superposition exactly analogous to the oscillation of neutrinos between flavors. The rate of this oscillation depends on the mass of whatever new particles mediate the baryon number violating process. Detecting neutron-antineutron oscillation would be direct evidence for physics beyond the Standard Model, and would provide crucial information about the baryogenesis mechanism. The experimental signature of neutron-antineutron oscillation would be spectacular. A neutron that oscillates into an antineutron and then encounters ordinary matter would annihilate. The antineutron would interact with a proton or neutron in the surrounding material, producing a burst of pions. Finding this burst of pions in a detector surrounded by ordinary matter, in coincidence with a neutron having been in the detector, would be the signal. The most powerful search to date was performed at the Institut Lau Langevin in Grenoble, France, using a beam of cold neutrons propagating through a magnetic field-free region for 8 seconds before hitting a target. No antineutron oscillation was observed, setting a lower limit on the oscillation time of about 10 to the 8th seconds. A new experiment, the NNBIR experiment at the European Spallation Source in Lund, Sweden, is designed to improve this sensitivity by a factor of 1,000, probing oscillation times up to 10 to the 11th seconds. If neutrons oscillate into antineutrons at any rate near the current experimental limit, NNBR will find it. The breadth and the ingenuity of the experimental program aimed at understanding the matter-antimatter asymmetry reflects the depth of the problem. There is no single measurement that will answer the question. The answer is hidden in the combination of measurements: the delta Cp of neutrino oscillation, the electron-electric dipole moment, the direct comparison of hydrogen and antihydrogen spectra, the searches for neutron-antineutron oscillation, the Cp violation in B meson decays, the constraints on the cosmological baryon-to-photon ratio from the CMB. All these measurements together constrain the theoretical possibilities, narrowing the space of allowed mechanisms until, eventually, only one remains. We have not reached that point. The constraints are powerful, but not yet decisive. The new physics that generated the matter-antimatter asymmetry has been elusive. It has not shown up at the LHC. It has not shown up in B meson decays beyond the Standard Model prediction. It has not shown up in the electron-electric dipole moment at current sensitivity. It has not shown up in the direct comparison of antihydrogen and hydrogen. Either it is there, just below the current experimental threshold, waiting to be found by the next generation of experiments, or it involves physics at an energy scale so high, or a mechanism so subtle, that direct detection is beyond the reach of any experiment that can be built in the near future. The leptogenesis mechanism, for example, involves right-handed neutrinos at masses of perhaps 10 to the 12 to 10 to the 15 GeV, far beyond the reach of any particle accelerator that has been built or is currently planned. The Cp violation responsible for baryogenesis in this scenario is completely inaccessible to direct measurement, knowable only through its low-energy consequences, if any. There is something philosophically profound about this situation. The question of why matter exists is ultimately a question about the initial conditions of the universe, about what happened in the first second, in conditions of temperature and density that will never be reproduced in any laboratory on Earth. The answer is encoded in the universe around us, in the baryon-to-photon ratio of the CMB, in the spectrum of antihydrogen, in the delta Cp of neutrino oscillation. But the encoding is subtle and the decoding requires experiments of extraordinary sophistication and patience. And the specific mechanism, the specific process in the specific model of the early universe that produced the asymmetry may be permanently beyond the reach of direct experimental test, accessible only through the indirect evidence of its low-energy residues. This does not make the question unanswerable, but it makes the answer harder to come by than most answers in physics. The history of physics is full of questions that seemed permanently beyond reach, and then yielded to a combination of theoretical insight and experimental ingenuity that nobody had anticipated. The detection of gravitational waves seemed impossible until it was not. The production and trapping of antihydrogen seemed impossible until it was not. The specific history of the matter-antimatter asymmetry problem does not yet include the moment of yield, but the experiments are running, the precision is improving, the theoretical landscape is being mapped. And the answer, when it comes, in whatever form it comes, will be the answer to the most personal question that physics has ever asked. Why are you here? Why is anything here? Why did the universe survive its own beginning? Paul Dirac found an extra set of solutions to his equation in 1928 and tried to explain them away, and when he could not, he accepted what the mathematics was telling him. Reality is more symmetric than it appears. The equations insisted on antimatter even when nobody was looking for it. Even when nobody had evidence of it, even when the predictions seemed almost too strange to take seriously, the equations were right. Antimatter exists, and its existence raises the question that Dirac's equations could not answer. If matter and antimatter are equal partners in the laws of physics, why is matter here and antimatter not? The universe produced an answer to this question in its first second, through some process we are still working to identify. The process tipped the balance by 1 part in a billion, let the rest annihilate, and from the residue built everything that has ever existed. You are the residue. Every person who has ever lived, every city ever built, every book ever written, every thought ever thought, all of it is the residue of a 1 in a billion excess of matter over antimatter that occurred when the universe was a fraction of a second old and hotter than any condition that has existed since. We do not know what caused that excess. We do not know where the asymmetry came from. We do not know whether the answer is in the neutrino sector, or in physics far above the reach of any accelerator, or in some mechanism we have not yet conceived. We are looking, with the most precise instruments ever built, in the most extreme conditions accessible in any laboratory, measuring the properties of anti-atoms that have never before existed long enough to study, trapping antiprotons in magnetic bottles, and comparing them to protons with sensitivities measured in parts per trillion. And we are alive to do the looking. Made of matter, not antimatter, by the grace of a tiny symmetry breaking in the first moments of the universe, here in the residue, asking why. That is the most extraordinary thing of all. The universe arranged its asymmetry precisely enough to produce something capable of wondering why it was arranged that way. The matter-antimatter asymmetry problem is the universe asking itself why it exists. And the answer is somewhere in the data, waiting to be found. We will find it. That is what the history of physics tells us. That the questions that seem permanent eventually yield. That the experiments that seem impossible eventually achieve their sensitivity. That the mathematical beauty that Dirac found in his equation in 1928 continues to reveal itself in the data of experiments he could not have imagined, in a world he could not have predicted, asking questions that begin with his discovery and end with the universe. The extra solutions to Dirac's equation were not a mistake. They were the reason you are here.